Thanks, Ray, for the invitation. Thanks to everyone who's taken part in planning this. The hospitality has been great, exceptional. I've eaten more good food in the last 13 hours or something than I have in maybe 6 months or a year. It's been fantastic. So I'm going to tell you about deep Gaussian processes for computer experiments. I'll introduce what both of those things are. I want to say that before I start out that this is Annie's work. Annie is a terrific PhD student of mine who is just about to accept the faculty position, but I shouldn't say where until she makes her final decision. But she has done terrific work on this project, and I think she's got a great career ahead of her. I've also worked with Dave Higgins, who some of you may know, and another student, Andy Cooper. So I listed my name first, but Annie's name belongs first. It's just first because I got invited to give this talk. So you get to hear it from me. All right, so I've broken the presentation down into 3 segments where I'm going to try to follow a similar format in each of the 3 segments. First, I'll introduce what a deep Gaussian process is, why we need one, what it is, and how we do it, different than some other people do it. I'll talk about active learning, which is also known as sequential design of experiments in the statistics community. And then I'll tell you about an approximation that a lot of you are already familiar with. I'm going to go kind of fast through that because I think of Texas A&M and Matthias Capitalist in particular when it comes to this part of the talk. And I don't want to mansplain to you about how to do this when you guys can hear it better from somebody else. But I think it's pretty cool and it's really nice in this application. Okay. What's a deep Gaussian process? Why do we need one? All right, I work in computer surrogate modeling, and I'll explain what that is in a second. But I think there are 3 areas of statistics where Gaussian processes are popular. You might even say they're the canonical tool. And those 3 areas are geostatistics or spatial statistics. So that's area number 1. I think that's probably where they were invented in the mining world in the 1950s. And then there's computer experiments, my area, I'll tell you a little bit more about in a second. And there's machine learning. It's just kind of a good general purpose prediction machine. And before deep neural networks became maybe the default prediction machine in machine learning, I think Gaussian processes were that thing. And for some problems, I think it's still that thing, although for others, we all know about the success stories of deep neural networks. So Gaussian processes are popular in those 3 areas. Mine is computer experiment. So what's a computer experiment? Well, imagine that you have a mathematical model for a complicated system. For example, you might be interested in modeling the drag experienced in low Earth orbit, where there's a small amount of atmosphere, and you might want to predict that drag for your satellite because you want to forecast where it will be sometime in the future, and that position will be impacted by the atmospheric drag that it experiences. So we can simulate atmospheric drag using the known physics and particle transport equations and things like that. We can accurately run a computer program and get the drag out, but that computer program is slow because what it's doing, and I'm not an expert at this, but like basically it's bombarding the satellite, the virtual version of the satellite with virtual particles of oxygen and helium and things like that. And if you do that enough and average and do a Monte Carlo, you can get a sense of what the drag would be, and that's computationally intensive. If you want to be able to use a simulator like that in real time, then you need what's called a surrogate model, because you can't evaluate that simulator in all possible configurations that the satellite might be in a trajectory and get the drag outputs that you want in any reasonable amount of time. So there's kind of like a resource problem. You don't have enough of the computing resource. So you have to conduct an experiment where you vary the conditions that the satellite might be in and see what the drag would be under those conditions, fit a model to it, and use the model to represent your understanding, to make a quick prediction for what the drag would be in a novel but representative circumstance, given the data that you have. So a computer experiment is not that different than a natural or ordinary experiment that we're familiar with in statistics, except instead of the data coming from a plot of land where you varied the amount of fertilizer and waited to see what the yield would be, that's the classic like Fisher experiment, you do it on a computer. You virtualize the system, and then you run the code and you get the output for different inputs. But then you do the same thing you would ordinarily do with a statistical model, is you fit a model to it, you fit a regression to it. In our world, regression has to be very flexible because the physical dynamics that you're studying with the simulator are highly nonlinear. So we need to fit a nonlinear regression model, and people call those models surrogates. You also hear people use the word emulator. The idea is that the fitted statistical model is going to replicate what the real computer solution of the mathematical problem would give you, only it's going to do it a lot faster. If your surrogate model can't do it faster, then it's not super useful. And it's going to give you appropriate uncertainty quantification. You have to be able to say what kind of an approximation it is. You predict this, and what's the interval? What could it be if you actually ran the computer code there? What would you do? All right, so that's I think I said all the things on the slide. What a surrogate is, it's just a meta model of data obtained from a computer experiment. We use it to make predictions, hopefully with good uncertainty quantification, so that we can use it in decision making downstream. Maybe we want to optimize something, or maybe we want to make a forecast of where something will be in the future. We need good predictions and good UQ. People are getting more and more ambitious in what they virtualize on computers. I see this happening all over the place. It used to just be in physics and in chemistry, but now it's in biology. I've even seen it done in economics and political science. People are entertaining what ifs using their computers, using simulation in a big way. And those models are getting very complicated. As those models grow in complexity and as we get more data from these simulations, we need to make sure that our surrogate models are able to capture the fidelity of dynamics that are exhibited by those machines or by those simulations. All right, that's a long introduction. I told you already that the Gaussian process is a canonical model for computer experiments and for machine learning and for geostatistics. What is a Gaussian process? It's a multivariate normal distribution for your data. So it's really a simple object. You probably used a multivariate normal for regression data before, where you said that y was Gaussian with a mean of x times beta and a variance of sigma squared times the identity, right? A basic linear model is a Gaussian process, but it's not what most people think of when you tell them you work with Gaussian processes. What they think of is this other multivariate normal, where my outputs y have a joint Gaussian distribution, but instead of the mean being x times beta, instead of the modeling action being in the mean, it's in the covariance structure. And that covariance structure is related to distance in the input coordinate space. So you're saying that your outputs, your y's, are correlated to one another by an amount that depends on the inputs, which has to do with distance. And here, if my function k, this is called a kernel function, if my function k is decreasing in its argument, often we choose exponentially decreasing, then I've got a covariance structure here that says I'm more correlated if I'm nearby and less correlated if I'm far away. So my outputs y are more correlated if their inputs are close together and less correlated if their inputs are far away. So this is kind of a conventional Gaussian process setup. It's just a prior distribution for the quantity of interest given its independent variable inputs. At the top, it says that the Gaussian process models are nonlinear and non-parametric and adept at uncertainty quantification. They're nonlinear because the form of the covariance is usually a nonlinear function. They're non-parametric because although I've introduced some tunable quantities, and you could call those parameters, but people would usually call them hyperparameters instead, they're not the important thing going on. The important thing going on are these distances, and I have as many of these distances, or at least as many distances, as I have training data examples. So the flexibility is manifest in this quadratic structure here of quantities that are learned from the x's. And I have n squared of those, or n times n minus 1 divided by 2. So this flexibility is growing with the training data size. So it's non-parametric. Uncertainty quantification, well, I'm going to have to show you that in a second. This is a prior. The posterior comes by viewing this as a distribution jointly for training and testing. So this is my training data. I've got my y's given the x's. If I posit the same relationship for my testing data set and make one big Gaussian distribution for training and testing at the same time, here's training, and then I just stack it for testing. And then I condition the testing data on the training data. Whenever I have a multivariate normal that's big and I condition one part on the other, I can do that in closed form. Usually we find that at the back of our favorite statistics textbook. Yeah.
A quick question about the non-parametric. It's called non-parametric because the key is the general function. Is this because of that?
I'm not going to say no because I don't completely understand it, but the way I think of it is
It's a key, a parameter or a function. K.
K is a function.
Okay.
Think about it as e to the minus, right? That's a good choice. E to the minus distance is the canonical choice for K. But a lot of K's will work, and what K isn't important. It's non-parametric because its flexibility grows with the size of the training data.
Okay.
That's not true for linear regression, right? The complexity is determined by beta, the slope parameter. But in this, the complexity is determined by the number of distances that you have in your training data set, which grows quadratically in the training data size.
Okay.
So that's the reason I think of it as non-parametric.
Thank you.
Okay, so I'm going to use it to model this data. This is an example of some XY data. It's clearly got a nonlinear relationship. In fact, it has two regimes, and I'll talk about why it has two regimes in a second, because I want to make a particular point about that. But the way that I fit these data is I make a grid in the input space that I call my testing set. That's where I want to make predictions. And I assume that the Y variables on that grid also follow this process. And then I condition from the observations I do have and use that conditional distribution to determine the distribution of my testing set. And I can do that in closed form. So if I take some testing locations, squiggly X, and assume they follow the same process, but what I want is the conditional distribution of that given training data, then that also follows a Gaussian distribution. And the moments of that Gaussian distribution have a closed form. It's like a linear projection, linear in this covariance space, but the Y variable is here interacting linearly with some quantity. And then I've got a covariance structure that's got a quadratic form. And if you squint at those equations, and it's not enough when seeing this the first time to really intuit what's going on, you can see fundamentally the way in which distance is involved. When my testing locations are close to the training locations, I have more weight in this calculation, and so I have a better prediction about what mu is. And when I'm making a prediction and I'm looking at the uncertainty or the variance, the closer my testing data is to the training data, the bigger this quantity is, the more negative it is, the more my variance is going down to represent learning. And then I get these equations. These are the dashed line is mu, and the intervals come from the diagonal of this covariance matrix with quantiles. So I get a nonlinear surface, and I get decent uncertainty quantification. Not perfect, because I probably have too wide of uncertainty here. So that's I think I want to point out about this data. All right. So the true data for that example is, this is the computer model. Imagine that it's just a sine and cosine on the left and a straight line on the right. But imagine this was a computer model that I was trying to learn, where for some parts of the input space, the dynamics are more complex or more interesting than in other parts of the input space where they're less interesting. And that's what this talk is ultimately going to try to exploit. And although the Gaussian process that I just showed you, same as the previous slide, does a decent job of capturing what's going on in this training data, it doesn't do a great job at realizing that there's some more structure here that it's interpreting as noise. And it's probably interpreting way too much of the structure out here as noise. Here it says shallow GP. You could also read ordinary GP. Ordinary GP and shallow GP are the same. I'm going to motivate a deep GP. which is an extension of a shallow GP. And just to kind of whet your appetite, I'm going to introduce a model that is an extension of what I just showed you that gets a much better fit to this data because it is able to realize that there's two different regimes going on and that different modeling dynamics are in play in each of those two regimes. That behavior, the two different things going on in different parts of the input space, it's covered up here, but if I push this, maybe we'll be able to see it. These data are referred, oh no, it just came, oh no, it's gone on my screen. Oh, here we go. It's over here. Okay. The Gaussian process in the middle is stationary because the only thing that it's using is a relative distance to do its modeling. It's looking at distance in the input space. I need to be also considering position in the input space in addition to distance, so I can get that the dynamics here are different than the dynamics there because this response surface is non-stationary. You cannot model it well by taking only relative distance into account. You need to take position into account too. This is a big area of research. People have tackled non-stationary Gaussian process modeling going back to the 90s. I worked in this area for a little while, but I want to focus on the last bullet here, which says deep GPs. Deep GPs were introduced in this paper in 2012, but it's very similar to an idea in this paper and another one that was basically from the late 90s. I know it says 2003 here, but people were working on this in the late 90s. The word deep comes from the machine learning literature. It's more modern, right? Nobody knew it. Nobody did anything deep back in 2003. We didn't know what that was. Deep neural networks is like 2010 or something. I'm just guessing. I'm not sure. And these guys in 2012 said, oh, you could do the neural network thing with Gaussian processes, and that would be pretty cool. But the idea was basically the same thing as what was proposed in 2000. And I'm going to tell you what that is. Okay. So this is a great picture, I think. Annie made this picture totally on her own. I think it's super insightful. So what I just showed you about this shallow or typical GP is right here. I have some responses that follow this multivariate Gaussian distribution. If I take a draw of y from this Gaussian, I'll have nearby locations more correlated than others as far ones, but based on Euclidean distance, and I might get a function that looks like that. Okay, so that's an ordinary Gaussian process. A deep Gaussian process, or a two-layer deep Gaussian process, arises when you take those outputs from the first Gaussian process and stick them in as inputs into a second one. So here the inputs were X, but now the inputs are Y. I've chained or convolved these two Gaussian processes together by sticking the output of one in as the input to another. And that's what's sort of being shown here. I've got this is the Y1s are my inputs, and it's giving me Y2s. And then I'm kind of throwing away the Y1s for this visual to show you as a function of the original X's what the Y2s would look like. And you can see that this relationship is more complex, right? Because I've done two Gaussian things. I've got one Gaussian thing going in as the input to another. The color here on the bottom is I think maybe the coolest thing about this picture. So if you imagine starting out with an evenly gridded set of X's, but you push them into the Y's and then make the Y's go into another set of Y's, the effect that has on the original inputs is to compress one part of the input space and expand on another one. So you can see that here, the X's down here are going to be compressed into the same Y1 values. The X's here are going to be stretched into disparate Y1 values. And then the X's over here are going to be compressed again. So compressed, stretched, compressed. I'm moving around my inputs, I'm warping them, and the word warping actually comes from those 1999 papers before deep Gaussian processes. So you're warping the inputs, in order to use position, so now position is involved because you move the positions of the inputs, and then when you use distance-based modeling in that regime, even if it's stationary, the effect you get is of a non-stationary model. And then you can keep doing that if you want. Here I'm showing a third warping or a second warping into a 3-layer GP, and you can keep going. Get a more and more complex.
Is there any connection with the Bayesian network? Because I feel there is some direction, the relationship.
With a Bayesian network?
Yeah.
Sure, I think you can represent this with a network, and I'm going to do that in just a second.
Okay.
In the same way that we do that with deep neural networks.
Okay. Thank you.
Okay, so here's sort of two views into how you would write this down maybe in a paper or on a slide. So on the left, I have a hierarchical model where my responses Y are Gaussian given some W's. The W now is like the Y1s and Y2s from before, but now I'm using the letter W, so you think warping. So these are my warped inputs. So Y given the warped inputs is Gaussian, and the coordinates of the warped inputs are also Gaussian given the original ones. I can have as many of these warped input coordinates if I want. So if I have a one-dimensional X to start out with, maybe I only want a one-dimensional W. So K would just go from just be one. So P would be one in the slide. But if I have a two-dimensional input or a three-dimensional input, maybe I want to warp all of the coordinates. So I would have three sets of these guys. Okay. Here's a diagram of that. My X's are going to some W's. These all represent Gaussian processes. These are the parameters involved in the Gaussian processes. And they combine as inputs into another Gaussian process to give you the Y's. It's kind of a neural network like architecture. This is for a 2-layer Gaussian process. If I have more, I could have more sets of nodes going across from left to right. How would I do learning or inference? Ultimately, I want to study the conditional distribution for Y given X, but I've got some W's in the way. So I need to integrate them out. I need to learn the settings of those W's, but in a Bayesian world, that's just integrating them out because they're a nuisance parameter. They're a latent variable I don't really care about. I don't want to know where these points warp to. I just want to make good predictions with the right warpings. So I need to do this posterior integration. I do have more on this slide, but I'm going to skip it. Some details that make it work in practice. I don't want to spend too much time. I always go kind of slow at the start of the talk, but things will speed up. All right, how do we do it? So I need to do this integral. We are not the first people to work on deep Gaussian processes. The machine learning folks, this has been very popular there. They kind of reinvented it. I told you that already. They really like fast inferential regimes, variational inference, expectation propagation, which is I think of as a variation on variation inference, Hamiltonian Monte Carlo. So these are all methods that are kind of modern. If you go back to 1999, none of these were available, or at least not popular at that time, so nobody was using them. So although the idea of a deep Gaussian process is quite a bit older than 2012, inferential regimes that are popular now are not popular then. So that's the reason they were reinvented. That's where the value was added in doing this integral more efficiently. Back in 1999, they were doing Metropolis Hastings, and it was kind of a nightmare because the latent variable is high dimensional. You can't integrate in high dimensions with Metropolis Hastings. The idea that we're going to use is it's also more modern than was available in 1999. It's elliptical slice sampling, but we are going to be in an MCMC framework. I like MCMC because it gives me good uncertainty quantification. That's important to me when I'm doing my surrogate modeling. Variational inference does not give good estimates of the predicted variance or covariance, but MCMC is great. So I'm going to do MCMC, but for the most important part, for this part, for the part involving a high dimensional latent variable, I'm going to use a modern sampling method. Interestingly, this paper is also from the machine learning literature. I don't know if Ian Murray would consider himself to be a machine learner, but he published this paper in ICML, no, AI Stats, in AI Stats, which is a machine learning journal. And it was published around the time that deep Gaussian processes were becoming popular, but nobody noticed it. And so they didn't try this, but they should have, because it works really, really well. So this is what we do. This is the elliptical slice sampling algorithm. You can write the whole algorithm down in a diagram like this, or if you want to go to their paper, they have an algorithm box and it's like 5 lines long. It's really simple. It's clever because it's a metropolis-like scheme, but it's joint for all of the parameters of your latent variables. And it's not doing a sticky thing where you reject and keep the previous value. It's more like a rejection sample. You just keep revising the proposal until you accept. And it works for anything that's Gaussian. I wrote Gaussian process here, but you could just write multivariate normal. Anytime you have a multivariate normal prior, you can do elliptical slice sampling, which is basically a weighted average of the prior draw and the previous draw in the Markov chain, which is accepted or rejected according to whatever model you're using. Here we're using multivariate normals for Gaussian processes, but when they wrote the paper, they used it for Cox processes and they used it for classification. So even though everybody thinks when you say Gaussian process, it must be that your data is Gaussian. Your data doesn't have to be Gaussian. The latent variable that you're using for modeling must be Gaussian. The likelihood that you use to accept or reject can be anything you want. So you can have any response distribution. They used it for binary responses. We're using it for other things that are Gaussian to make these Gaussians chain together so we can learn the latent variables. If you reject, then you just revise the weights on this combination and keep going until you accept. This is super easy to code up. I gave it to a summer school of students in France this summer, and they all did it in under an hour. I gave them the likelihood so they didn't have to write them themselves. They just coded up the elliptical slice sample, and it works great. You don't have to do that though. We made some software. So if you want to fit a 2-layer Gaussian process with some data X and Y, we can do that for you. In fact, I'm going to show you that live in an R session. So here I always set the C because I don't want to be surprised by I'm going to build the data, same data that we were doing from before. So I'm really just building this data set. Okay. And for comparison, I'm going to fit a 1-layer GP. So this is ordinary or shallow Gaussian process, 5,000 MCMC iterations. And make a prediction for you. I'm skipping some of the steps in the file because they're not necessary. So here is the fit to that data. A little different than before because of some of the defaults in the package that are a little different than when we made the slides. Here's a 2-layer fit. It's a little slower because it's doing more work. It's doing this elliptical slice sampling that the 1-layer doesn't have to do. The same number of MCMC iterations though. And then I'm going to make a plot. And it's going to be a little different than what I showed you on the slide. And the reason for that is that the defaults were different in the package compared to what I did to make the slide. But you can see that it's now picking up on the extra wiggliness here, and the variance is reduced. If I just use the back button. I didn't talk about that. I will in a second. That's the fit from an ordinary Gaussian process, and that's the fit from regular deep one. This intermediate plot that I forgot about is showing you the mapping from X to W, and that's what I have on the slide too. So I'm just going to go back to the slide. This is the fit I showed you before, a little different because we tweaked some of the parameters to get it to look different. And these are the W's, so X to W. So you can see I'm stretching out the first part of the input space and flattening the second. So I'm stretching out here and flattening here. Yeah.
I ask a quick question regarding the elliptic slice sampling. So when now we reject a sample, you keep it in the Markov chain, or you just do not record it?
You do not record it. You only stop that loop after you've accepted one, and you throw everything else away. Yep.
I also have a question about this. For this elliptical slice sampling, it looks quite similar to the MH algorithm, Metropolis Hastings algorithm. And what's the specific reason? Because your algorithm already has the MH to learn the hyperparameters. What's the advantage you use this one instead of the MH?
I still use Metropolis Hastings to learn the hyperparameters, but hyperparameters, we're talking about like 3 or 4 quantities.
Yes.
Here, we're talking about a vector with the length, the size of my training data. So if I have 1,000 training data locations, this is a 1,000 coordinate vector, and I need to sample from all of it. If I use Metropolis Hastings for that, I'm either going to have a very high rejection rate by proposing all of them at once, or I'm going to have very poor mixing if I propose one coordinate at a time. This solves that problem. It does the whole vector at once. You're right that this looks like Metropolis Hastings, but a Metropolis Hastings would either accept or reject and move on. And if it rejects, it's going to take the previous one as a copy, which is going to make the mixing of the chain form.
Oh.
But I go through this loop until I accept. I don't keep any previous value. That's what Ray was asking about. So it's a rejection sampler, not a Metropolis sampler. Because Metropolis would have the previous state copied if you reject it.
Here, if you reject, the last one will get to some formula and something like this.
That's right. So you're updating these lambdas. You're basically making the window closer so that you give more weight to the previous one and less weight to the novel one, the prior one.
Let me see. Thank you.
Here's another view on a different test problem. So this is a 2-dimensional test problem called the G function. It's kind of wacky. It's a function of 2 inputs. It's flat in the middle and rises up steeply at the edges. This is one sample of a 2-dimensional W. So here's the first coordinate of W and the second coordinate of W, both as a function of the 2 input coordinates X. Here's another view of that. It's showing you how X's in the original space are being warped into the W space. I like this better because it kind of shows you where the points are going, how it's compressing some of them and then spacing out others in 2 dimensions. It gets harder to visualize in higher dimension. So I can't show you this in like 4 dimensions quite as easily, but I can still run a little comparison. This is a 4-dimensional problem. So 4-dimensional inputs, 4-dimensional latent layer. Training data sizes of 3,000, 5,000, and 7,000, where I'm looking at RMSE, smaller is better, and I'm looking at continuously ranked probability score. Again, smaller is better. The deep GP for every problem size class is lower than the ordinary GP. It's more accurate and it's better on UQ. The continuously ranked probability score is taking accuracy and uncertainty quantification into account. And it's really good on that. Yes.
This might be a rather naive question, so forgive me. But the fear, so going back to like that picture you had where you had the regular shallow GP and it showed that nice smooth curve, and then you have the two layer GP and it shows, you know, the finer details of the signal. Is there a risk of overfitting?
Sure.
Okay.
Yeah. It helps that we're in a Bayesian framework, and so there's some natural regularization.
Yeah.
And I could have, I could loosen that up by having some of the Gaussian processes be less well constrained. That was part of the slide I skipped back there. You wouldn't use the same Gaussian process in this context as you would on its own. You would use a more flexible one on its own. In the context of multiple Gaussian processes being chained together, you want them to be regularized. Yeah. And then I can go for deep Gaussian processes, but we've tried that, done 3 layers, we tinkered with 4, and nothing has beat 2 layers in our empirical. So you want to regularize it. It's the right instinct. You totally can. Yeah. All right, so that was 35 minutes on the first component. Why? Non-stationary flexibility is important in some situations. Ordinary or shallow Gaussian processes don't do great. You can do better. by functionally composing layers of these things. And you can do the inference with MCMC using elliptical slice sampling, and there's an R package. All right, now I'm going to transition into active learning, which is how to train these things efficiently. A nice thing about computer experiments that sets them apart from natural experiments is that you have much more control over the experimental plan. Right? I can just decide which inputs I want to put into my computer program and run them. That's a lot easier than trying to tell someone who's doing agricultural yield to vary their fertilizer. And they're only going to be able to do that once a year, and you're going to have to be limited to what fertilizers are available on the market and so on. So I have more flexibility in planning the experiment. I'm gonna sort of make a look at the picture here rather than the slide. So let's say I'm trying to model this function. This is the true function. There's some observations, and I might fit a Gaussian process to those observations. So here's two different ways of fitting them. One of them is by maximizing the likelihood, and the other is by posterior integration with MCMC. And you can kind of see that neither of them are ideal for this data, at least ideal at getting what the truth is. One of them is maybe overfitting, that's what I think, but still kind of capturing what's going on. And the other one's maybe a little bit underfitting, especially in this area where the relationship is similar. Okay, so a deep Gaussian process is better at this because it's able to see that it's flat here and curvy there and also here. And I'll show you one of those fits a little bit later. But perhaps the most important thing is that you can readily see that I need more data to find out what's going on here than I need to find out what's going on there. So if I have the ability to plan the experiment, I want to learn what parts of the input space are hard or interesting, and what parts are easy, so that I can allocate my run budget to put more runs where it's hard and fewer runs where it's easy. So I want to do some kind of active learning. Active learning is the idea of creating a virtuous cycle between data acquisition and learning. The old-fashioned term for that is sequential design of experiments. So I want to create this virtuous cycle where I might start with a small experiment, 10 runs or something of X's and Y's. I'll fit a model to that, and I'll use that model to tell me where it's deficient. Okay, so I want to create a criteria that lets me choose the next input to run. Then I will run at that input and get the output, and then I'll augment my training data set, refit and repeat. So I want to create this learning and data acquisition cycle. And it's kind of a greedy or stepwise, a little bit like that, one at a time. This is a whole enterprise. There's lots of ways to do this depending on what you're trying to accomplish. What I just want is a good fit everywhere. And I'm going to measure good fit by predictive uncertainty. So if these are my predictive equations, I've shown you these once already. They're Gaussian with a mean and a variance. I've simplified the variance to be pointwise instead of joint. But just to remind you that we have these in closed form. You'll notice that the variance function does not depend on y. This is crucial. You don't need to know what y is to know what your uncertainty is. You need to know what y is for the mean, but not the variance. And since you don't need to know what y is, you can entertain what it would be if you added a new row to your design matrix. So if I was going to add a new x to my existing x's, I could deduce how uncertainty will go down. You can always do this for Gaussians, even one-dimensional Gaussians. You know what the value of your data is before you get it. And then I can take that and integrate it. So I can take this future variance function and integrate it. It turns out this can also be done in closed form. Another reason why Gaussians are popular. You can integrate their variances on pen and paper and get a mathematical expression for that doesn't have an integrated. People call this the integrated mean squared error, or sometimes people put a P in there, integrated mean squared prediction error. I could ask, what is the coordinate x1 that minimizes this integrated error? That would be a good one to choose, because that's going to give me the most bang for my buck when running the simulator. It's going to reduce the variance the most. So that's a really good choice. I might want to do Bayesian optimization and choose the one that minimizes the predictive mean. That could be cool too for a different problem, but I'm not going to do that. Although we have done that. This has also been entertained in the machine learning literature for neural networks, actually back in the 90s, where they cannot do the integral in closed form, so they do a sum-based quadrature instead. It has become part of the Gaussian process literature as well, so we include it, but I'll show you that it's not a perfect approximation in our context. All right, so if you do that with these fits, so here's the two fits I showed you earlier, it's kind of uninteresting. It's uninteresting because it's not telling me what I hoped it would tell me. I hoped it would tell me that it wants points in this region, but it's telling me where, this one's telling me it wants points out here, maximized here and there. Not more here and less there, which isn't really what I wanted. Same thing here, it's more or less telling me the same thing. It wants a point either here or here, not more here and less there.
For
Yes.
the sequential design, did you use the conjugate family property such that each posterior is always normal distributed, right? It is like this.
It is a conjugate family. If you want to incorporate one more training data point, you would also have a Gaussian distribution. So it's conjugate in that sense.
Then how do you do the sequential design? Each step, each sequential corresponding to one layer, or how do you?
Not layers. I'm just adding one more training data point. When I add one more training data point, the predictions will still be Gaussian. They were Gaussian before I added that training
Oh, I
data
see.
point, and they're Gaussian after. So it's conjugate in that sense.
Okay.
I'm not sure that's what you meant, but I
So
am.
the sequential design is like the prediction here. You're adding more data points. Each
Yes.
data point that you add is a sequential, and the like a design like that. Okay, thank you.
All right, so both of them are telling me something uninteresting, but I just want more data away from where I had data before. Each one of these downward spikes in this cone is at a location where I have a data point. And I want more data in between. I want one at most here, but once I get one there, it's going to be somewhere else in between where I didn't have data before. And that's kind of uninteresting. The reason that's happening is because my Gaussian process is stationary. All it cares about is relative distance. If I wanted to care about position, then I can use a deep Gaussian process, which is deliberately blocked out there. So if the surrogate is stationary, sequential designs will end up space filtered. So I want to apply this with a deep Gaussian process. And it's super straightforward. I only have really one slide on how to do it. All I have to do is map through my hidden layer. So if I'm entertaining a new X, I might want to add this one, and I want to know what its contribution to the integrated mean squared error is. The first thing I have to do is find out what it is in terms of W. So I need to make a prediction through the hidden layer to get a W. Then I need to evaluate the criterion like IMSE on that W. And then I need to average. I need to do that a lot of times in my MCMC to take a ergodic average. And then I can do that for any of the locations I want to see which ones are more valuable than others. And again, we have this in the code. This is exactly what it does. After you do the fit, you can ask it to evaluate this criteria or the other one I was telling you about that comes from machine learning. So I'm going to just do that really quick. That was the next part of the slide. So I'm going to fit it first for an ordinary Gaussian process and then for a deep Gaussian process. Okay, so, and then I can make the plots. I better start pasting the plotting code here. Maybe I can make this a little bigger so it's easier to see. This is the running example from the R code. With a one layer GP, it's kind of boring. It says I want, actually the way we have this is for minimizing, not maximizing. So it would choose a point at the edges. This one would choose a point in the interesting region because it's much lower in the first half of the space than in the second half of the space. So it's learning that the inputs are stretched here and compressed there. So I need more data here than I need there. And for the example in the slides, which is a little different, I need more data here and left it out here. And this is the approximation is not as good out here because I've worked at the inputs and I've messed up the quadrature that was being done numerically. But if you do the integral in closed form, you get basically 0.0. All right. We've done some comparisons to show that, and I'm only going to give some limited ones here, that indeed you get more samples in the green region with a 2-layer. You get more samples there than you do in other parts of the input space. If you track accuracy over budget, the deep GP with IMSE, that's the red one here, makes the most rapid progress. If you look at score, it rises the fastest, makes the most rapid progress. I'm going to go quickly through this. We did the satellite drag one, where we showed that we get down to a certain accuracy faster than if we don't use the deep Gaussian process. So this is ordinary Gaussian process. This is 3 variations on a deep Gaussian process with different numbers of layers and things. They all work about the same. So we learn faster when we have a higher fidelity model and when we choose the inputs where the model wants them.
So Bobby.
Yeah.
Interesting to see the comparison between the ordinary GP and the TGP. I remember when we published the TGP about 15 years ago, one of the motivations also handle the non-stationarity.
Yes.
At least you argued in the paper, you were able to do that better than the ordinary. So how come it doesn't? Really
Yeah, so how come it doesn't beat,
Yeah.
maybe it beats the ordinary GP a little bit, but that's a good question. So I didn't want to get into this, but TGP handles non-stationarity through divide and conquer. It makes axis aligned partitions in the input space and fits different Gaussian processes to different regions. That works really great when the response surface has axis aligned regime changing behavior. But this problem does not. This is a nice smooth change of behavior in the input space that's not along the axes. It's hard to visualize that because this is a problem in 7 dimensions. So I'm not sure how to show you that, but I think that's the reason. If it's axis aligned regime changes, TGP works well. If it's not, then the smoother convolution of Gaussian processes works well.
because of the partition of the tree region is parallel to the axis.
The data have to have that. If the data had that, then the tree is perfect. But in this case, I think the data don't have that. Yeah.
It's a 7 nodes means it's the dimension of X is 7, it's like this.
Yeah, there are 7 inputs. That's the dimension of X.
Okay.
Our default is to have the dimension of W also equal the dimension of X. So 7.
Okay.
So that would be 7 nodes. But we also looked at 3 nodes, 5 nodes, and it's like close. This is a zoom in of this part of the plot. 7 does the best. 5 does almost the same, and 3 does a little worse. A question I often get is, maybe you want to try doing an autoencoder. An autoencoder is where the latent layer of your neural network is narrower, has fewer nodes than the input layer. And this has been shown to be really good in some situations where neural networks are involved. But I have not yet seen one with deep Gaussian processes, where you're kind of funneling your inputs through a lower dimensional space. So far, we haven't seen any evidence that that works.
Thank you.
So I have this sequential design. So like when you are sampling a new point, do you already have some data points or you are starting from the very beginning?
We always start with something. If you want to start with 0, that's possible, but I haven't been able to get that to work great. I always like to start with something. So if you have a n-dimensional input space, maybe you want to start with like 100 points, which is like roughly 10 per coordinate. That's kind of the rule of thumb that people have used in the literature. Or if you're in a 2-dimensional space, maybe you want to start with 20. So you just pick random 20 or space filling 20 to start out with to kind of bootstrap or jumpstart this whole process.
I was thinking that if you start from 0, will it even work? Because then maybe you just get stuck in that smooth like fat region.
I think if you start with 0, then you have to have a very well thought out prior, and you have 0 data. We always like to talk about like non-informative priors or weak priors. You cannot have one of those if you're going to start with absolutely nothing. So that's the reason I prefer starting with something, and then you can have some default priors that work well for small data sets. And then as you grow your data, have less and less influence when the training data set gets. All right, I have 9 minutes, but that's almost by design. I'll skip this little summary slide. So the Vecchi approximation, if you guys don't know what this is, you should all talk to Matthias, because he's got like 15 papers on it, and I can't make sense of most of them. I've got the high level description of it, and so does my student. And when I say I can't make sense of it, it doesn't mean I think it's bad. I think it's really insightful. Everything that I do understand, I'm like, wow, that's super cool. And then there's that other stuff that I'm not really sure what that is, but it's probably also super cool. So what is the Vecchi approximation? It's a way to handle big data. You have to work with a Gaussian distribution with n dimensions, which means that your covariance matrix has to be decomposed in order to evaluate the likelihood or to make a prediction. And that's hard. That's a cubic runtime cost, which means it's prohibitive to do it if you have more than a couple thousand training data points. And I already showed you examples that have 7,000, and I want to get to 100,000. I'm not going to be able to do that with cubic matrix decomposition. So the Vecchi approximation, I'll skip this slide again from time. Other people have done other things, but I think they're not as good as the Vecchi approximation. So what is the Vecchi approximation? It starts out with an identity that says that any joint distribution can be factorized as a product of one-dimensional conditionals. Okay, so this is a basic fact of joint or conditional probability, characterized for 3 random quantities. You can do that with the likelihood. So if you have a likelihood over capital N quantities, you can decompose it as a product of one-dimensional conditional likelihoods. Again, this is an identity. It works for any ordering of the data. It's an equal sign. Here I've introduced some notation for the indices of that conditioning set. Where here, the ith conditioning set has all the indexes less than I, so that it will look just like this. That's not the Vecchi approximation. That's just 2 facts about joint probability. The Vecchi approximation says that you can short circuit that and probably still do a good job. You'll have a good approximation if you reduce the size of this conditioning set to a subset. So take a subset of those conditioning variables, potentially a very small one of size m. And if you do that, it'll be a lot faster. And maybe it won't be too bad as an approximation. In the case of a Gaussian process, we need to evaluate this likelihood. And this likelihood is univariate Gaussian, and its mean and variance components all have nice, tightly closed forms. They're all like little predictions. I'm trying to make a prediction to get what the ith component is given the components that are indexed earlier than I in the line. If I do that, then I've converted a cubic in n problem into a cubic in m problem, and many cubic in m problems. So if m is really small relative to n, this would be a huge savings. It goes even further than that, but I'll want to spend even less time on this. The Cholesky decomposition, which is the most common way of decomposing a big matrix with Gaussian distributions, the Cholesky of the precision matrix, or the inverse, is sparse. And you can directly write down what that Cholesky decomposition is, or what this Cholesky factor is. In fact, you can populate it in advance in parallel before you do any other calculations. And again, I'll skip the graphic here because of time. That means that everything you would want to do with a Gaussian process, like evaluate its likelihood or sample from its prior, or make a prediction, can be done directly on this sparse Cholesky factor and not on the original variables. So I'm using sparse matrices, I'm using parallelization, and that's probably what that's it. Sparse matrices and parallelization. 2 things that make stuff fast. Okay, so what am I going to do with that? I'm just going to apply that at every layer of my deep Gaussian process. Everywhere I've used a Gaussian process before, these are my equations from earlier, I'm going to swap in a sparse Cholesky factor version using the Vecchi approximation. So everywhere you see a sigma W, I'm going to figure out what the U's are for that covariance matrix, and I'm going to use it instead. Same thing over here. Inside my elliptical slice sampler, I'm going to do it too. And I've got a fit true two-layer function. You specify Vecchia equals true, it will transparently to you use these U matrices, which are sparse, instead of using the dense decomposition. And it's super fast. I'm going to skip this slide and just show you how fast it is so we can finish in less than 4 minutes. This is the cubic scaling of prediction and training. So the training and then prediction. So you can kind of see that it's getting way slower in terms of seconds per 1,000 MCMC iterations. With the approximation, it is linear or essentially free. It doesn't take 0 seconds. Just think about it, it's more like 10, 20 seconds, depending on the size. But not 5,000 or 25,000.
So is this for a regular GPU or deep GPU?
This is for the deep GPU. Okay, we did some comparisons to other methods from the machine learning literature. Using variational inference with approximations that involve inducing points. I don't love inducing points, and I didn't tell you what they are. I think this is a particularly bad combination. It's fast, but it's not accurate and it lacks fidelity. Hamiltonian Monte Carlo is a great method in general, but I think in this case, this approximation that they're making is not the right thing. Our method, which uses the Vecchi approximation and elliptical slice sampling, is the best of all. And we make some comparisons to shallow Gaussian processes where that's feasible. And so actually the results I showed you earlier came from the Vecchi approximation. So all of the circled ones, I showed you those earlier. I just didn't tell you they were using the Vecchi approximation. When I can make a comparison to an ordinary Gaussian process, my ordinary Gaussian process is better than its Vecchi approximation. So you do lose something by making a Vecchi approximation. But if you go deep with the deep Gaussian process, you gain again. So you're winning the comparison. I can only do this ordinary Gaussian process when there's 3,000 data points. With bigger ones, we did even try. Here, our Vecchi approximation is beating the Gaussian process counterparts, so the D and GP, ordinary GP. Same is true everywhere. These box plots up here are for the machine learning methods based on variational inference. They're just not competitive, in my opinion. They're very different plots. I'm not sure why that is. Because they have some examples where they seem to work well, but the ones that we tried. All right, last thing. We did it on the satellite problem that I introduced earlier. We did it up to 100,000 training data points. We just wanted to demonstrate in this that deep Gaussian processes were more accurate than ordinary. So both of these are using the Vecchi approximation. Both, I think, are essential for working with data of this size. They're using the same underlying idea. The only difference between this one and that one is this is chaining two Gaussian processes together. This is not. So you get the extra accuracy bump. Same thing with UQ. The UQ is again more impressive. You get a much better view of uncertainty with the deep Gaussian process when you take variances into account than you do. I didn't even put the variational methods on this slide because they were awful. They had numbers upwards of 30% for RMSE. So this is way up there. Wasn't even on the, we didn't put it on the sheet. All right, so that's it. Vecchi approximation gets around cubic bottlenecks in Gaussian process methods, and they port over nicely the deep Gaussian processes. We're imposing sparsity in the precision matrix and in its Cholesky decomposition, which works really nicely in this setup. So I want to end there because it's exactly 3 o'clock. Everything that I showed you is fully reproducible. This is really important to me in my research. The package is of course on CRAN, but all of the examples are not really in the package because they're too complex to be examples in the docs. But we have all of the problems, the satellite drag, the G function, everything we've done is in this Git repository, including the demo, this thing is there too. So thanks very much again. I'm sorry for going into